Hello and good morning or afternoon or evening, depending on when you are watching this. A couple warnings to go over prior to us getting into our discussion on periodic trends. Take a moment and read over this. All right, on to our next one. All right, so biggest thing here is we want to make sure that we can make sure we get the what, the how, and the why. And obviously, you need to be able to tell me and explain the what, the how, and the why. The biggest mantra, the most important mantra that you can have for periodic trends is size of radius versus strength of nucleus. I'll say that again. Size of radius versus strength of nucleus. That will be a very good starting point when you are trying to compare one element to another one, or if you're ranking multiple elements based on a periodic trend. So one more time, size of radius versus strength of nucleus. So for our periodic trends, we have a few. In this first video, we're going to get into a couple of them, and then in the second one, we will finish off the other few. So first thing we need to look at are these two effects. The effective nuclear charge, otherwise known as Z effective or ZEF, and the other one is the shielding effect. So effective nuclear charge is basically the relative attraction that the valence electrons, actually all the electrons, but our focus here is the valence electrons that the protons have for the nucleus. And we know the nucleus attracts all electrons in an atom, but all of our trends are determined, and we look at them starting with the valence electrons. I think we all know valence electrons are the outermost electrons in any given atom. So all the electrons are actually going to feel a little bit of a different pull. The closer you are to the nucleus, the stronger the attraction is going to be. The further you are from the nucleus, the reduced or diminished the attraction will be. Now, the shielding effect is pretty straightforward. Think of a shield back in the Roman Empire. What was the purpose of a shield? It was there to protect you, to be between arrows coming at you and you, so you wouldn't be killed. It's kind of the same idea, what you see in the image here to the right. Those inner electrons are shielding the effect of the nucleus to those outer electrons. There's a bit of repulsion going on, as you can see with the red arrows, that kind of diminish, as I said, the effect of the attraction of the nucleus. So they kind of work together and against each other, but ultimately, the more electrons you have between the nucleus and the valence electrons, the more diminished the effect is going to be. Conversely, the more protons you have, if you do not change the number of electrons in between the valence electrons and the nucleus, the stronger the attraction is going to be. And we're going to see both of those aspects. So ultimately, we are referring to the feel of the nucleus, which again is the attraction between nucleus and our valence electrons. So, kind of an idea here of what a shield can do to protect the valence electrons so they don't feel is much of a pull. So how do we calculate Z effective? Well, here's a lovely equation. It's just Z minus S. Pretty straightforward, where Z is the nuclear attraction or number of protons. So all you got to look at is the atomic number. S is all electrons in the atom that are not, I repeat, not the valence electrons. So they are inner core electrons. There are a total number of electrons in the atom, but we do not include valence electrons in that calculation. So ultimately, number of electrons in the previous noble gas plus any D's or F's electrons, if there are any, past the noble gas. So you put these two things together and you can get an overall integer number. Now, keep in mind in the real world, the Z effective is actually going to be a decimal number. There's a very long, drawn-out calculation based on energy levels, which we're not going to get into, we're not going to worry about, but it still exists. But for our purposes, we're going to deal in whole number integers. Makes it easier that way. So let's take a couple examples here to calculate our Z effective. We'll look at magnesium. You find magnesium on the periodic table. We know it has 12 protons. And we look at its number of electrons from the previous noble gas, which is 10. Now, we know magnesium has 12 electrons total, but again, we do not count valence or the highest energy level. So those 3s2 electrons we're not going to worry about. So 12 minus 10 equals 2. Now, interestingly, what's the charge of a magnesium ion? It's the same as the Z effective. So yes, while there's a calculation we can do, the Z effective is also going to match what the possible charge could be. All right, aluminum, again, 13 protons. Again, it's also previous noble gas, is neon, or 10 electrons. And then we do our calculation, 13 minus 10. Now, interestingly, aluminum and magnesium are in the same period of the periodic table. So they have the same number of inner core electrons. They have a different number of valence electrons, which leads to a different Z effective, which now can prove that aluminum is a smaller atom than magnesium because the valence electrons are pulled in harder because there is a stronger attraction from the nucleus. A +3 Z effective versus a +2 Z effective is a larger number, therefore it's a stronger attraction. Any questions on Z effective? All right, our first trend is the atomic radius, to figure out the direction of it, the what, the why, and the how. Very important concepts. So what is the atomic radius? It's just half the distance between two nuclei. Obviously, we can't measure to the edge because orbitals and atoms, they have no edge. It's not tangible. It doesn't exist. So when two atoms are bonded together, like a diatomic hydrogen, we know it's just half the distance from a mathematical standpoint. Right. The how. Well, the box to the right is representing a periodic table. So we know the radius is going to increase as we go down a group. We know the periodic table is going to increase from right to left. So ultimately it has this type of arrow right in smack dab in the center that we are going to increase towards the lower left-hand column. Therefore our smallest elements should be going towards the top right. Yes, we know hydrogen is actually the smallest one, but most periodic tables, hydrogen and helium, they're raised above the periodic table, so they're not really taken into account. But yes, hydrogen is still the smallest. All right, we've got to our Y. So we know it increases down, and we're going to look at it decreasing to the right, even though the arrow we just saw shows it also increasing to the left. So for decreasing to the right, we're adding a proton. The nucleus is getting bigger. And adding a proton compared to adding an electron going left to right, it's a bigger change. Protons they're much larger. We already talked about that back with atomic structure. Excuse me. Now, more protons, because there's a larger nucleus, pull those valence electrons and all the electrons closer in. It's a greater effective nuclear charge going left to right. If it's a greater Z effective, everything's pulled in tighter. The atom itself has to get smaller, again going left to right. Now, there's not really an increase in shielding, because when you go left to right, as we saw with our example of magnesium to aluminum in the same period of the periodic table, you're not adding any inner core electrons. There's no new energy levels. So you're adding electrons to the valence shell at the same time you're adding protons to the nucleus. As we said at the top, it's a bigger change for protons than adding electrons. Now, going down a group, here we have adding energy levels. So every time we add energy levels, we know it gets bigger. Adding more energy levels puts your new valence electrons further and further from the nucleus, therefore making it a larger radius. Inner electrons keep the valence electrons from feeling the nucleus. That is our purpose, or that is the purpose of shielding. Those outer valence electrons, they don't feel the pull as much. They actually have the ability to get further and further away, but of course they do not fly off. And if you notice from a Z effective calculation, as you go down a group of the periodic table, I lost my train of thought. The Z effective stays the same. So keep that in mind, that Z effective is staying the same as you go down a group. Our ionic radius mostly has the same reasons we just saw. Atomic radius, ionic radius, same idea. Obviously, what we're looking at is the radius of ions. We know cations have lost electrons. We know anions have gained electrons. But now we have to look at how many electrons are lost in the cations and how many electrons are gained in the anions. So to lose 1 or 2 or 3, to gain 1 or 2 or 3 will control your size. Cations are always going to be smaller than their parent neutral atom. Anions are always going to be larger than their parent neutral atom. Right. Looking into the Y again, cations get smaller, reduced repulsion. There's less electrons, less repulsion. If you lose enough electrons, you could even drop to a new energy level. So if you remove an entire energy level that had electrons in it, you're going to be that much smaller. From an anion perspective, you're adding extra valence electrons. The number of protons is not changing, But those little bit of added valence electrons adds repulsion between electrons. Therefore, it's gonna get a little bit bigger. Questions on this? Isoelectronic species. Pretty straightforward here. Atoms and ions that have the same number of electrons. All these examples have the same configuration as neon. And as you can see, they all are different elements, and they all have a different number of protons. Electronically, they're identical, but can we figure out why magnesium is the smallest of this group? That's right, it has the most protons and the least electrons. It has to be the smallest one. Questions on this one? Okay. As we said, increased protons can pull harder on the valence electrons, greater attraction, greater effective nuclear charge. So ultimately, the radius will be smaller than those with the same number of electrons and energy levels. So again, these three are identical these five are identical electronically, but they differ in their number of protons. All right, ionization energy, the next trend to look at. The root word of ionization, ion. So this is the energy to create an ion. Well, here we are. What is ionization energy? The energy required to remove an electron from a neutral atom of an element. And we're going to add to that in the gaseous state. You are only able to remove electrons from a given atom in the gaseous state. Again, on the right is our box representing the periodic table. We know it's going to increase ionization energy as you go up a group. We know it's going to increase ionization energy as you go left to right. So overall, ionization energy should be the most at the top right and the least at the bottom left. Again, not including hydrogen and helium, they don't count. We know noble gases are actually the highest, but again, they have 8 valence electrons. They don't want to gain any. They don't want to lose any. They don't care. Just leave them alone. They're fine. They're happy. They're stable. So, as we can kind of see here, atoms that have more electrons, or more valence electrons, tend to have higher ionization energies. It's more difficult to remove them. Things that have less valence electrons, it's a lot easier to get them to a noble gas. They have low ionization energies. So, down a group. Well, we know that the electrons are further from the nucleus in higher energy levels because the radius is getting larger as you go down a group. We're also going to have an increase in shielding as you go down the group. So the pull on those valence electrons is lessened, it is decreased, it is diminished. Well, if that's the case, then it should be easier to remove electrons. Questions on why for the decrease down a group? Going to the right. Well, closer to having a full stable valence shell. Plus, the radius is getting smaller. The valence electrons are closer and closer to the nucleus. It's a stronger attraction. Increase Z effective, stronger Z effective, stronger attraction. If it's a stronger attraction, it's that much more difficult to remove electrons from an atom. Questions on ionization energy? All right. So if we look at this chart for a second, which you don't need to copy the chart, if we were to take one element and remove one electron at a time, that's why we get ionization energy 1, 2, 3, 4, according to this chart. Now, the purpose of this chart is we're looking for the very large jump in energy. And as you can see right here with sodium, 496 to 4,560. Pretty big jump there. Magnesium, 738 to 1450. That's doubling. That's not much. But if I go 1450 to 7,700, that's a pretty big jump. Let's look at aluminum, 578 to 1800, okay, about 3 times or more. And then 1800, lost my mouse, to 2750, 1,000 or so more. But then 2700 to 11,600. What we're trying to see here is, where does the ginormous jump occur? We know sodium is in column 1. It has a 1 plus charge. We know magnesium is in column 2. As an ion, it's a 2 plus charge. We know aluminum is in column 3 or 13. It has a 3 plus charge as an ion. When you remove 1 electron from sodium, 2 electrons from magnesium, 3 electrons from aluminum, you ultimately become a noble gas on the previous energy level. If you were to then try to remove the next electron from the previous noble gas compared to these elements, you've changed energy levels. You're that much closer to the nucleus. The attraction is going to go up. There is less shielding for the same number of protons. So that big jump actually tells you how many valence electrons excuse me, are in any given element. You look for the big jump. Everything prior that has small little jumps in energy, they're all in the same energy level. The ginormous jump is a change in energy level. Questions on that idea? All right, we're going to stop here and we'll pick up the rest in the second video. Thank you.